Good morning, everybody. I'm going to go ahead and get started. Welcome to part 2 of the webinar covering simulation in Creo. Before we get started, just got a question about part 1, about the recording for part 1. I wanted to apologize. During part 1, I indicated that the recording would shortly be on YouTube, and it appears that that still has not happened. So I'm going to make sure that I look into that immediately after this webinar. To the person I didn't reply to about that, I'm very sorry. I was waiting for that to get uploaded and I just never ended up seeing it. So I'll be sure to look into that shortly after this presentation. So with that out of the way, welcome again to everybody. In this webinar, I'm going to be going into some intermediate skills in Creo Simulate. So specifically, I am going to be covering some structural analysis tools that I skipped over last time. So we're going to be looking at idealizations, we're going to be looking at welds, we're going to be looking briefly at nonlinear materials. Additionally, I'm going to be jumping into thermal analysis. I'll talk a little bit about the difference between steady state and transient. And I will also take a look at mixed structural and thermal analyses. And additionally, I'll look at other analysis types as well, so buckling and modal analyses. Lastly, we will do Q&A. If anyone has any questions, feel free to ask them whenever you want in GoToWebinar. I'll try to get to those questions immediately, but if I don't, I will have Q&A at the very end, and I'll get to everybody's questions then. So my name is Sebi. I've been working with CAD for about 11 years now. I've been with PDSVISION for about 5 years. Here at PDSVISION, I specialize in simulation, design, routed systems, a whole bunch of random stuff, to be honest. And I come from a mechanical engineering background. PDSVISION, my company, is the largest global PTC partner and reseller. We have offices all over the world, as you can see. We've come a long way in the last several years, expanding our operations. And now we can pretty much offer support anywhere on the globe. As far as what we support, mostly PTC products, but we are a licensed ANSYS partner and reseller as well. There are some other programs like KeyShot, like SimonSoft, which is actually a PDS app, like Moldex 3D. These are going to be other pieces of software that we support that we think fills some sort of niche that PTC products do not fill. Lastly, what really makes PDSVISION stand out is our excellent team of technical resources like myself. Specifically, our simulation team is very good and very capable. We're able to support all of the different simulation apps, as well as ANSYS, standalone ANSYS as well. Okay, so with that out of the way, I'm going to start talking about simulation. So first, I want to just do a quick review of part 1. This webinar was about a month ago, I want to say. In this webinar, I covered what simulation is. We talked about how it's a huge value add. It's going to save you design time. It's going to save you money. Through saving you time, through making a better product, through reduced need of testing. You don't have to break things manually if you're able to simulate that process, or at least you can cut your testing down. So there are a whole bunch of benefits to using simulation, to understanding how your part for assembly is actually going to behave in the real world before you spend all of the time and effort manufacturing and testing. There are many tools in Creo that are related to simulation, but I think there are 3 main ones. At least if we're talking structural type simulation, so the ability to do static analysis, if you apply a force to something, what's going to happen? There are really three tools in Creo that we have access to. Those are listed here: Creo Simulate Live, and Creo ANSYS Simulation. Of these three, we talked exclusively about Creo Simulate in the last demonstration. We are going to be continuing that today. So we're going to be staying in Creo Simulate. We are going to be hitting Simulate Live and Creo ANSYS in coming webinars. Just to briefly recap the difference between the three, Creo Simulate is the oldest. It's been around a long time. It has a big set of features. Creo ANSYS is a newer tool that incorporates ANSYS solver directly. This is kind of an exciting up and coming tool, but it lacks some of the features that Creo Simulate has because it hasn't been around as long. Simulate Live is a totally different type of thing. Simulate Live is going to run very quickly, and it can run automatically with design changes you make right in Creo. So Simulate Live is meant to be done as kind of a first step as you're designing the part to get very quick results. And then you can go forward with a different tool like ANSYS, like Creo ANSYS, like Creo Simulate to get more detailed results when the time comes. So those are those three tools. And as I said, we are going to be jumping into the other two in later webinars. In addition to that, there are several other Creo extensions that are simulation related or simulation adjacent. There is Fluid Flow, so Creo Flow. That is a really great extension if you do any kind of fluid modeling. I also want to add Simulate Live. Does handle fluids now as well. So we do have a lot of people that are using Simulate Live for kind of a first pass of fluid simulation, and then jumping into either Creo's fluid extension or ANSYS to get more accurate results at that point. We have generative design in Creo as well, which allows you to apply certain loads and constraints and then generate geometry that will best or will lower stress in that scenario. Generative design is really cool because it can be used with 3D printers to generate geometry that would not be really manufacturable using traditional methods. And we have mold design in Creo as well. I'm sure I'm missing some others in here, but there is a large suite of products, you know, as far as simulation related things. But these three, Simulate Live, and Creo ANSYS, are the main three in terms of structural simulation. We talked about the licensing tiers of Creo Simulate last time, and I want to briefly review by pulling up this chart. Creo Simulation Elite, which is the first column here. This is going to be available to most people at this point. Simulation Elite is going to be included with Creo Design Essentials, which is a tier 1 subscription license. So Simulation Elite is really exciting because a lot of people have access to it and they don't realize that. I think that change was made around 2020 or 2021. PTC added Simulation Elite for a whole lot of people. Going to the second column, Simulation Extension. That is going to cover a lot of the tools we talked about today. So modal analysis and buckling analysis, steady state thermal analysis, and shells and idealizations. Those are all going to be covered in this middle license tier. Lastly, we have Creo Advanced. That's going to cover combined structural thermal, which we're going to talk about today. It also includes pre-stress, it includes nonlinear materials, it includes transient thermal analysis. So there are certain features today that I'm going to be showing that do require these advanced license seats, either the intermediate column or the advanced column. Last time you'll remember I tried to keep the demonstration to Simulation Elite features. And lastly, in my part 1 demonstration, I talked about the 5 basic steps that we're going to go through when we run a simulation. We have to do this every time. That's going to be apply a material, create idealizations, generate our mesh, add constraints, and add loads. So we're going to be continuing that process today as we bring in additional features here. Okay, so first I'm going to talk about some additional tools for structural analysis. The first of those are idealizations. Idealizations are going to simplify your model. Examples of those include shells, beams, springs, and masses. What they're going to do is they're going to replace geometry in your model with some kind of idealized shape. An example, or the most common example I would say, is a shell idealization. What this is going to do is it is going to take a very thin model. Sheet metal models are very often used here, like we see in the image, and it is going to squish those models down into a single plane. So those those green surfaces you see on the screen, those are actually 2D. Those are completely squished down so that they have no thickness whatsoever. What Creo is then going to do is it's going to generate a two-dimensional mesh, and it's going to run the simulation. The simulation time is going to be drastically reduced. The advantage of all of these idealizations is they're going to allow your simulations to run more quickly. Shells are generally going to be used when your thickness is about 1/10 the length and the width. So you can see with this model right here, it's a very thin model, so a shell is going to apply. A beam is going to be used when you have a very long model, like a beam with a constant cross section. That beam is going to be simplified down into a one-dimensional line, so the trajectory of the beam, and a 2D cross section. Again, the advantage here is your simulations are going to run much, much, much faster. Spring idealizations are going to replace springs. So instead of actually breaking that spring down into tiny chunks, we're just replacing that spring with an equation. And same with masses. Rather than actually meshing a big piece of mass, we can simplify that down into a single point or multiple points, and replace that with just a single value. Masses specifically are often used to replace complex geometry. For example, if I want to mesh the structure, or I want to determine the structural characteristics of a car body, I'm not really going to be concerned with the specific build of the engine. So oftentimes what people do, if they're just trying to simulate the car body, you can replace the engine with a mass. Basically, we're saying we don't care about the geometry of that engine, but the mass it has is still important to us. So all those are going to simplify our geometry. They're all going to make our simulations run much faster. Will it decrease the quality of your results? The answer is probably. So if I was to make a mesh for this model on my screen, spend the time to make that mesh good, enough elements like we looked at last time, and then ran this, it would probably take 10 to 100 times longer, but we would probably get slightly better results. So inherently these idealizations, they are going to usually make your results a little bit worse. The exception here is with springs. I would never recommend actually meshing a spring. And oftentimes that will actually get you worse results than just using a spring idealization. But most of the time, these are just going to be time savers. They can, of course, make your results better if you make your results more specific in other ways. So maybe you use this idealization, but you run multi-pass adaptive. So your analysis goes through more passes. In that way, you could probably get better results in the same simulation time by using these. In other words, they are very efficient ways to decrease your simulation time. it's often going to be a smart idea to use these, even if your goal is the most accurate results, if that makes sense. Next, I'll talk briefly about welds. But the main thing I'm going to say about welds is that they're not going to be usually used in the way you would assume. Welds in Creo are mostly used to join together shells. So just going to jump to Creo really briefly here. All right. And I'm going to jump into this shell model, and I'm going to view my shell surfaces. And we'll notice that these two shells have a gap between them. There's a bit of space between those two shell features. And the reason for that is that the geometry is condensed down to the midplane of each of these parts. So even though these two pieces of metal are touching in the real worlds, when I simplify them down to shells, they are no longer touching. So how do we handle that? We make a weld feature to join these two together. So that is the main application of welds in Creo Simulate, to be honest. It is through joining together these shells. If you are someone who works with a lot of welds in the real world, and you are trying to simulate those welds accurately, what I would recommend to you is I would recommend that you read a specific paper that the Army released. You can find this thing by just Googling US Army Creo Simulate weld paper. You can find this on Google. And it is a very good paper covering the best way to model real welds. I'll jump down to the end just to kind of summarize the findings. But long story short, if you have the time to do it, the best way is to actually model the weld geometry as a solid and then create a contact interface, a nonlinear contact interface. Interfaces are something that we're probably going to cover in the next part of this webinar series. But the main takeaway here that I want to get across is that the weld feature in Simulate is mostly used for shells. It is not really used to actually model welds. If you are interested in simulating welds, read this Army paper. They will tell you the best way to do it. All right. Lastly, I just want to briefly mention nonlinear materials. This is a big benefit of Creo Simulate. It has been added into Creo ANSYS as of Creo 10, but Creo Simulate Live still doesn't have this support. So for a while, the only tool that was out there in the PTC realm that could do nonlinear materials was Simulate. These are supported. They're going to be created in the material library. You're going to be able to assign your different structural characteristics in each direction, X, Y, and Z. And then when you load that into Simulate, you're going to assign a material orientation for your specific application. The other analysis types I'm going to be talking about are modal analysis and buckling analysis. And thermal, but I'll cover that on the next slide. Modal analysis is going to deal with vibration. Every single item in the world has several of these natural frequencies. For example, when I pluck a guitar string, no matter how hard I pluck that, it's going to make the same notes. It's going to vibrate at the same frequency. So your parts and assemblies in the real world work this way too. They have these certain frequencies that they will resonate at. That's where vibration can get out of control and can cause damage to your structure itself. If you're interested in how vibration can cause failure, I would recommend looking up the Tacoma Narrows Bridge on YouTube. I'm not going to show this video today because it's 10 minutes long and I don't want to use the time for it. But this is a bridge that experienced resonance over a few hours that led to total bridge failure and collapse. So modal analysis can be useful in determining these natural frequencies. So for example, if we know that at 25 Hertz, this thing is going to resonate, that's something we can take into account. And secondly, buckling analysis. Buckling analysis is going to be useful anytime we have very slender supports with compressive axial loads. So if you imagine a Greek column holding up a building, this is the exact case we're dealing with. This is going to be a very long and thin support, being that it's a column, and it's going to be under a compressive load. So the load is going to be, straight up and down, and it's going to be compressive. So it's going to be, pushing downward in the case of the support. Anytime you are dealing with those situations, anytime you are simulating those type of situations, you are going to want to take buckling into account. Buckling is a separate failure condition. So when we're doing a normal static analysis, the usual failure condition we're looking at is the tensile yields condition. That's where the stress of the model exceeds the material's maximum. That's going to be the usual cause of failure. But anytime we have this buckling situation, so a long thin support with compressive axial loads, anytime we have that situation, we have a second failure condition that we have to worry about. Not only can we hit that tensile yield stress, but additionally, we have to keep in mind that this thing can buckle as well. It's a separate thing that we have to test. Buckling can happen after a failure due to stresses, or it can happen before. It's just something you need to simulate to find out. Buckling is particularly dangerous because it happens suddenly. When a model usually fails, you'll notice some deformations. There's a graph of this process that you can look at, but essentially this thing is going to bend and show some signs of wear and tear before it actually breaks. That's how things usually work. But for buckling, this is not the case. It just happens suddenly. Additionally, buckling can be caused by material imperfections. So if this is something, if you're getting bad quality steel, then you're going to want to be more worried about, because that, little imperfections can make buckling much more likely. So those are all the reasons that you're going to want to start simulating buckling if you're not already doing that and you're dealing with, compressive axial loads on narrow parts. And lastly, we have thermal analysis. Creo Simulate offers both steady state and transient types of analysis. Steady state is basically time equals infinity. That's how I like to think of this. So if I turn on my computer and then I walk away for an infinite amount of time. So I walk away for, let's just say 3 months, and then I come back and I look at my computer. What temperature is this thing gonna be? So, after 3 months, we can assume it kind of reaches its steady state temperature. We can come back and say, okay, the CPU is 120 degrees Celsius. These are just examples, but that's what steady state is referring to, that infinite amount of time. What the system is going to approach, the temperatures it's going to approach at an equilibrium, so just over the course of time. Transient is different because that is going to be what happens over a specific period of time. So I turn on this computer and I come back 20 minutes later and I want to know how warm this thing has gotten. Lastly, we can do mixed structural and thermal analysis. In this case, the heats that we're going to be modeling in our thermal analysis is going to cause actual deformations in my parts. You're probably aware that when something heats up, it tends to expand. Materials are no different. So when we apply heat on this circuit board heatsink example that we see on the screen, this is actually going to warp my model. This is going to cause it to change its shape, going to change its size. that is going to apply stresses and forces. And this is something that we can model in Creo Simulate. This is called a mixed structural thermal analysis or combined structural thermal analysis. And it does require an advanced license. All right, so I'm gonna jump into my demonstration now. And I'm gonna pick up where I left off in this sheet metal example we see right here. So you'll remember that last time I mentioned there are 5 steps that we want to go through every single time. The first step, well, it doesn't really matter the order too much as I implied, but the first step will be apply a material to my model. So in this case, I'm going to go ahead and assign stainless steel. The second step is to apply loads and constraints. So I'm going to go ahead and apply a constraint on this edge. Oh, gotta select edges. There we go. Step 3 is apply my loads. So I'm going to go ahead and apply a load again to an edge. And you may remember step 4 was create our idealizations. We didn't do this at all last time in part 1 because I said that this step was optional. So this model right here would definitely benefit from a shell idealization. A shell is going to be used, as I said, anytime your thickness is much smaller than your length or your width. Rule of thumb is 1/10. And beams similarly are going to be used anytime the length of a specific item is greater than 10 times the length or the width of the cross section. So that's a rule of thumb you can use. I'm going to go ahead and detect shell pairs. Can pretty much automate this process. Now, if I go to idealizations, we'll notice that these shell pairs have all been created. I mentioned that this is going to compress this down to a single 2D surface, and we can view that in our review geometry. We can see the shells that have been compressed down. Now, when we make our constraints and loads with the shell, we want to be careful. If we put them on the top or bottom edge, everything will work properly. This will be condensed down to the edge of the mid surface. But if I applied the constraint or the force to one of these side surfaces, that's going to give me a problem because when I condense this down, that surface is not going to exist anymore. So one thing to keep in mind with shells is you want to apply your forces and constraints on edges. Okay, lastly, I pointed this out in my demo, but we have a problem here of the shell surfaces not touching once they're condensed down to their mid surfaces, as we see here. So I would need to create a weld feature to join those two together. I have a few different options for welds. I can create a weld that joins together edges. So basically takes this entire edge and joins it to this geometry. That would be a parameter weld. Or I could do a spot weld where I select specific points to weld together, just like we were doing a spot weld realistically. So I can go ahead and select this surface and this surface. I can select a point to weld. I can select the diameter of the weld itself and material. And we'll notice that these two pieces of sheet metal are now connected in that area. If I mesh this, so that was step 5, create my mesh. We'll notice that this is meshed with 2-dimensional shapes. So quads and quadrilaterals and triangles are going to form this 2-dimensional mesh. And this is going to be much, much simpler than meshing this in 3D. So if I did not create a shell, I would have many more elements than 65. Okay, so that is shells or idealizations in general and welds. As I mentioned, if you want to model actual welds, so fillet type welds where I would weld along this edge right here to join these two together, the most accurate way to model that is not going to be using this weld feature. And this is where I would recommend the Army paper. So Google, US Army simulate weld paper, and you will find it. As far as nonlinear materials, so those are going to be created here in materials. Default is going to be isotropic, but I can do orthotropic or transversely isotropic. This allows me to configure these materials with each of the values in different directions. And then when I go to actually assign those materials in Simulate, I'm going to be asked to set up a material orientation. This is going to allow me to flip in the X, Y, or Z direction. So set a material direction as some variation of X, Y, and Z. And I can apply angle rotations to that as well. So rotate about some degrees. This lets you set the material orientations in this X, Y, and Z plane in Simulate to correspond with the material directions that you set up in the materials window. Again, this takes an advanced license, but it's going to be really useful if you want to use that functionality. The next thing I want to show is a modal and a buckling analysis. In this case, we have a long beam, and you'll notice the force that I've already applied to it. I've constrained the bottom of this in all directions, and I'm applying a compressive axial load, as we see here. This is a perfect example of a buckling case, a case where you want to keep buckling in mind. So if we check out analyses and studies, this is just a static analysis. And I can go ahead and view the results. And I'm just going to change this to PSI because I know the failure condition for steel in PSI. We'll notice that the maximum stress from this loading that I set up is about 41,560 PSI, or about 41.5 KSI. Steel is going to yield at about 50,000 PSI. I think it's 51 or something like that. So this is about 4/5 of the way to a failure. Not going to quite fail, but we're definitely getting close. Now, with the same example, I'm going to set up a buckling analysis. So I'll do new buckling. We're going to need to select an existing static analysis. So that one I just ran. I'm going to bump up these buckling modes to, we don't need 16. Let's just bump it up to 4. And okay. Now, if we go ahead and analyze this, we'll notice that our results are shown in terms of buckling load factor. What this is telling me, anything below 1 is going to experience a buckle. This 0.206 is telling me that this thing is not just going to buckle, it is going to, we're basically exceeding that value by 4 times. So just for reference, this thing would not fail in the traditional sense. In terms of tensile yields, this thing would not fail, but this thing is going to basically fail 5 times over due to buckling. So that just kind of emphasizes that we are always going to want to show buckling or test buckling in any case where we have compressive axial compressive axial load case. It's always going to be a good idea to check this. With review deformed, this is not to scale, so it's not like this deformation actually means anything, but this is how this thing is going to bend, how it's going to fail. This first case is how we would assume it's just going to kind of bend how we would imagine, but we can look at these other buckling cases. And we can see this thing will actually buckle differently under different loadings potentially. All right, so now with this same case, I'm going to run a modal analysis. A modal analysis is going to determine my natural frequencies. So this is going to be able to help us figure out if our model will resonate. And that resonating can cause damage to our model, as I've implied. So we'll go ahead and do new modal. Modal analysis is going to be independent of my loads. So we actually don't need to apply loads to run a modal analysis. As I mentioned earlier, if you pluck a guitar string, no matter how hard you pluck it, the results, the natural frequency, the resonance, it's going to be the same. The same note comes out of that string. So for the same reason, we don't need loads. That's just going to change the scale of our results, but not the actual frequency itself. Constraints are optional, but they are going to change our results. So if I constrain this thing on the end compared to whether it's just floating in space, those are different scenarios. They're going to give us different results, but we can run either or. So I'm going to run this constraints, and I'm going to show 16 modes here. And we're going to run this. And this is going to give us a list of the different natural frequencies that my model is going to resonate at. So we'll see the first is at 0.85 hertz. We actually have two there because my model is symmetric. So it's going to give me two results for a lot of these values. We have resonance again at about 5.31 hertz, 14 hertz, 22, 28, 46, 66, etc. If we take a look at these modes, so how this thing is actually going to vibrate, some of them are going to look a little bit weird. If we look at my first mode here, we can see that this is going to be the initial resonance experienced, or at least the lowest frequency value. I can go through these as well and see how this thing would look. Okay, lastly, I'm going to show a thermal analysis. So here we can see that computer board example that I had set up. I've already applied a convection condition to this entire model. But I'm going to take a second and talk about what that means. So just as in structure mode, we can see that we can just switch between structure and thermal mode right here in the ribbon. But just as in structural mode, we're going to have 5 steps again, 5 required steps, and they're pretty much going to be the same thing. So just as before, we're going to assign our material. Instead of our loads, we are going to have heat loads. This is going to be any heat that's going to be generated into our model, usually in the form of watts. So energy per second that is emitted. Something like our CPU here, our computer chip is going to constantly be generating heat. Additionally, instead of constraints, we are going to have boundary conditions. These are going to be prescribed temperatures. So if I say, the screw that screws this in is always going to be at 25 Celsius, something like that, I can apply a prescribed temperature over here. We also have convection conditions. This is how most cooling is going to happen with any part. When the air moves against it or a fluid moves against it, that's going to cool it off. So just like a constraint, we're going to set up a convection condition. This is what I had already set up for us. So if I just expand this out real quick, we'll see I manually selected all of these surfaces highlighted in green, and I applied convection to them. That's why I didn't do it in the demo. It's a lot of clicking to get each of these fins. But basically that says convection can happen there. We can also apply radiation if we have an advanced license, but I'll say that if you're dealing with temperatures that we normally deal with here on Earth, like a hot circuit board is going to be whatever, 100 something degrees Celsius, then radiation is going to be pretty negligible. Radiation doesn't really have much of an effect until you get to like the cosmic temperature scale of like, stars that are whatever tens of thousands of degrees. Radiation for something like the circuit board is going to be less than 1%, probably much less than 1%. So most people honestly choose to exclude radiation unless you're working in space. There are, I'm sure, some exceptions. But just to get the point across, radiation is going to be negligible most of the time. Okay, so I have my condition set up, my convection condition. So that acts like a constraint. I have my materials assigned as well. So the heat sink is aluminum, the computer chip is epoxy, and the board is nylon. And now I'm going to apply a heat load. I'm going to apply that across the entire component of my CPU. And that is going to be a 1 watt heat load. Okay. The last two steps are going to be the same as structural, so I can set up idealizations if I would like. I'm not going to do that in this scenario. And I can mesh my geometry. If I do not mesh my geometry, it will do it automatically with default settings. All right, so now my thermal analysis is set up, and I can go ahead and run this. So I need to do file new, and I can do new steady state thermal or new transient thermal. I'm going to do steady state. So basically how hot this thing is going to get. If we say time equals infinity, we give this thing all the time in the world to heat up. What temperatures is it going to approach? I'm going to go ahead and run this. If we look at our results, we'll notice this is going to be shown in temperature rather than something like displacement or stress. We're going to be able to look at temperature, temperature gradient, temperature flux, or heat flux. But these concepts are kind of analogous to what we were looking at in structural. So instead of displacement, you have temperature. Instead of heat loads, you have instead of forces, you have heat loads. Instead of stresses, you have heat flux. Most of the concepts are kind of analogous, if that makes sense. So we'll see that the highest temperature is right on my chip where that heat is being emitted. The board is going to be a bit cooler, and the fins are going to be a bit hotter. All right, very cool. Now, as I said, as this thing heats up, it is actually going to apply structural, static forces. This is going to deform my model. And that's due to the fact that when things heat up, they are going to expand. So if we would like to do a structural analysis based on this heat information, that's going to be called a combined structural thermal or a mixed structural thermal analysis. We can do that. The way we're going to do that is we're just going to jump into structural mode. 3 of our steps here will already be completed. So we already have a material assigned. We've already done idealizations or not done them. And we already have a mesh. So all that we need to do is loads and constraints. Now constraints is should be obvious. This thing is going to be bolted in here. So I'm going to constrain all of these holes. Okay. Now the load, we are actually going to be getting that load from the thermal analysis. Basically, we're saying that the load applied is the load due to the expansion due to the heat. And the way we do that is by using this MEC/T load to bring in results from a thermal analysis. We'll see that I can select my thermal analysis that I should have named something more creative. And I do have to put in a value of a reference temperature. Basically, that's the temperature of the air, the temperature of your room. So reference temp, I'm going to use 20. Okay. Now I can go ahead and run this as a structural analysis. So I can file new static. And I'm not spending a lot of time in here because I talked through this, this window a whole lot in the last example. Clearly, we should name this something a little bit better. Additionally, I've been running single pass adaptive analyses. Just to quickly review, this is what you should use for a more quick results set. Multi-pass adaptive is going to give you much more accurate results, but it's going to take more time. It's going to run the same simulation multiple times to get those accurate results. So single pass adaptive is a good middle ground. Quick check, the results should never be trusted. The only use of quick check is to make sure your simulation completes. So we'll notice the run completed, and I'm going to go ahead and show displacement and show deformed. Clearly, this is going to be exaggerated, the deformation, but we can see what's happening. Let's turn that scaling off so it's not quite as exaggerated. We'll scale it just 10 times beyond normal. So we'll see this board is warping, it is behaving that way due to the heat. If we want to see what that looks like in terms of stresses, we'll notice that does put stress on these fasteners. So I am getting a pretty high stress here, maximum stress of 29 megapascals. And that's just due to the expansion of the board, putting stress on these fasteners. This is something that we should be concerned about in this scenario, since we are getting such expansion of this circuit board. Right, and that is all I've got for my demonstration. In the next part of this series, I believe the plan is to do one more on Creo Simulate, where we're going to cover some advanced tools like design studies, and then get into these other tools like Creo Simulate Live, Creo Ansys, and generative design. So I hope to see you next time. Just wanted to mention, we are back up and running for training. Reach out to us. We're happy to support you wherever you are in your Simulate journey. If you're just figuring out you have Creo Simulation Elite, or whether you're already using 4 of these tools to use, for different parts of your design process, we're happy to help. We're happy to support you. We're happy to help you in your Simulate journey. So I'm going to go ahead and open it up to questions. As I said, these videos should be going on YouTube. The last one never made its way to YouTube. I will get that all settled. but I would assume this is gonna go on YouTube sometime or another. I'll give you an update as soon as I have that. If you have any technical questions for me, feel free to ask them right now in the Q&A. Otherwise, feel free to reach out via email for anything that you don't think of immediately. It looks like there is a comment that was put into audience with the YouTube link. Maybe I missed it. Maybe that's my fault there. But you all should be able to see that in GoToChat. So part 1's on YouTube already. You can check that out. And part 2 will be up in the next couple days. So sorry about the confusion there, everybody. But yes, they will be on YouTube. You should have the link. And I believe that is our only question for today. I'll give it just another minute in case anybody thinks of anything, but otherwise feel free to reach out to me. You have any questions about this stuff. If you think you should have access to Simulate, if you think you should have Simulation Elite, but the button doesn't work in your ribbon, common problem, also reach out to me. Happy to. Okay. Thank you again, everybody, for joining this week's edition of PDSVISION Webinar Wednesday. Hope you all have a great rest of the week and hope to see you next time.